gone now. Yeah.
Okay, yeah, I can see a
Good.
recording button.
Okay. Thank you.
Okay, great. Okay. So sorry for the slow slow start to today's class. Okay. Hopefully this is going to work. No, not that. Definitely not that. That. Okay, can you see my screen?
Yes.
Great. Okay, so we can get started now with the maths. So what we're going to do is basically work through some standard functions from chapter 6. So we'll be on page 88, I think, onwards of the notes. So chapter 6, some standard functions. Now, these are probably functions that you know. They're functions that you know and you've used, and they're in fact functions that we've used already a lot this this semester, but we're just going to review them and review the different properties, but hopefully there's not too much new material here. So the first category of functions that we're going to review are the logarithmic and exponential functions. So we're going to review the logarithm first, and using the logarithm we'll then define the exponential function. And as I mentioned, I mean, these two functions are functions that you know. So we're about here in the notes, and I suppose what's strange with a lot of these functions is that they're quite abstract, okay, and that somebody at some point defined them or sort of invented them, but they did so in quite an abstract way. So let me try and get this theorem pasted. Okay, so the logarithm function is defined through this following theorem. Okay. Through no, the logarithm function, the theorem. Okay, so we've got the following result, which is a theorem that I don't think we've seen this semester. It's quite both a useful theorem and how can I put it, one that's quite abstract and actually quite difficult. So what it tells us is that if you have an interval of I of r and you have a continuous function, then you can define a primitive for your function. Okay, there exists some functions such that f prime is equal to f. So it's a theorem related to the existence of primitives. Now, as you can sort of guess from what you know, there are many cases where you can have existence through, how can I put it, through sort of calculation, through calculations. So if you take polynomial functions, you can find f, the primitive, quite explicitly. But for other functions, you can't always see the explicit expression that easily. But this theorem is how the logarithm function is defined. Okay, so it's defined as, God, I'm not starring today. It's defined as follows. So if we take the function that maps x to 1 over x, so it's used as follows. Okay, we take the function that maps x to 1 over x, which is a very simple rational fraction. In fact, no, was it doing that? That's a continuous function on r plus star. Okay, it goes to minus infinity 0 plus and plus infinity 0 minus, but what's important is what happens on r plus star. And what we do is call natural logarithm, so log of x, the primitive of 1 over x, which is equal to 0, 1. So that's how the logarithm function is defined. And so you can see that this definition really is quite abstract. But that's how somebody someday basically defined the logarithm. Now, we have a bunch of properties that you've seen before for the logarithm function. So these properties are the following. So we're considering the function ln, but by I guess abusive notation, I often write that log as well. So it's increasing on 0 plus infinity. That's the first important sort of thing. It's differentiable and even C infinite on 0 plus infinity. And of course, due to how it's defined, it has the following derivative. And then you have some quite pleasing properties. So the logarithm of the product is the sum of the logarithms. The logarithm of the ratio is the difference of the logarithms. You've got similar nice properties for powers. So if you take the logarithm of a to the power n, you get n log a. And similar, if you have a power that's a sort of a fraction, we have some limits. So it goes to infinity at plus infinity, minus infinity at 0. And we have a limit here. Now, I think you probably know all of these properties, except perhaps the C infinity thing, because C infinity is a space that we defined only this year. Do you know the limit? Have you seen that limit before that's in sort of 0.6?
I didn't.
Okay.
Didn't either.
Okay, so it's probably new for you. I can show you, well, not, I won't be able to show you all the steps of how it's derived, but I can tell you that the proof, so sketch of proof of 6, just so you have an idea of where it comes from. Okay, so the key point is something that's proven in an example in your notes. So on page 88, example 6.18, it is proven that if you take x greater than 0, x minus x squared over 2 is smaller than logarithm of 1 plus x, which in turn is smaller than x. So we saw part of this example yesterday, I think, because we saw this bound, this upper bound, and in this example, so I think it was just slightly further on, and it's the example I didn't detail, but it's in your notes and uses techniques that we went over yesterday. You can find this lower bound for logarithm of 1 plus x. And we're going to be able to use these bounds to prove this limit. So, in particular, if we take x strictly positive, we want to basically exclude 0 because we're going to divide by x. We have 1 minus x over 2, smaller than logarithm of 1 plus x over x, smaller than 1. Okay, so if we divide by x, we have the following bounds. And this should give you an idea of how we get the limit. How we get the limit result. So can you see anything that happens here if you take x to 0, for example, here and here?
On both sides.
Exactly. Yeah. So we get, if I sort of detail it a bit more, but we get limits when x goes to 0 plus of 1 minus x over 2 is 1. Limit x goes to 0 plus of 1 is of course equal to 1. So through this squeeze theorem or the théorème des gendarmes. So through, I think it's called the squeeze theorem in English, and we get the result. So we get limits when x goes to 0 plus of logarithm of 1 plus x divided by x is equal to 1. So that's where this new sort of property comes from. So what we can do using this function is maybe graph it. So graph of the function x maps to logarithm of x. So we're only going to work on r plus star, so we only need the sort of right hand side of a graph. Okay, now what we know about this function is that it's increasing. Okay, so I guess we could do a variation table, but it would just show us that the function's monotonous on r plus star, so we don't really need to, we wouldn't gain that much information on it here. But I suppose if I put, for example, 1 here, 2, 3, etc., we can try and get some further information on the logarithm that will help us graph it. So we know that x maps to ln of x, increasing on r plus star. We know 2 limits. This is all written above, but you've got the limit, no, not a minus infinity, 0 plus of logarithm of x is minus infinity. The limit at plus infinity of logarithm of x is plus infinity. Okay, and to help us graph it, we can compute a tangent. In particular, we're going to compute a tangent at 0. No, not at 0, at 1. So at 1, logarithm of 1, that's equal to 0. Okay, so if I draw the curve in red, eventually we'll have the curve going through that point. And we can compute the tangent. So the tangent at 1 is given through the following expression. So you've got the expression for tangents in, I think, definition 6.12 of this chapter. So you know that the tangent to a curve, the equation at a point C is f of c plus f prime of c times x minus c. So here c is equal to 1. So you have y equal to f of c, which is logarithm of 1, plus logarithm prime of 1, x minus 1. And again, we can simplify this a bit. You get 0 plus 1 over 1, so 1 times x minus 1. So it's x minus 1, the tangent. And so we can sort of roughly draw the behavior. So x minus 1 behaves something like this. So the tangent at 1 will behave like that. So that allows us to slightly, I suppose, refine the behavior of the function. If you want to plot it really precisely, you can compute further values, but they're not always going to be, I guess, that precise, the logarithm. For example, I can tell you that logarithm of 2 is roughly 0.69. So based on my my graph, I guess it will be roughly around there at 2. But then we can try and plot the function. So it roughly behaves like this. I don't quite like the part on close to 0 here, but I think you get the gist. Yeah, let's just say it behaves like that. It's probably flatter, but roughly you have something like this. Okay, that's a rough sketch of c of the logarithm. It's not the most precise curve, but it gives you an idea of the behavior. One thing that's important is that as it goes to minus infinity at 0, this part of the curve becomes quite vertical. Okay, but you've probably seen the graph of the logarithm many times before, hopefully. And so probably much more precise than this one. So that's it for the logarithm function. And based on the logarithm function, we can define the exponential function, which is also a function that you know of. And so it's defined using the following property, which again is something that I think is quite new, and that I don't think you've proven yet. I may be wrong, but it's an inversion property. So it's something to sort of take as true for now, but you'll prove it, I think, further on in your sort of maths classes. So if we take a continuous and increasing function, then one thing that you know, based on things that you've defined in Math 0, is that f is a bijection from I to the interval j equal to f of I. So for example, the logarithm function is a bijection from r plus star to r. Okay, the logarithm function maps all positive values of r to values across the whole of the real line, and it's a bijection in doing so. And as it's a bijection, there's going to exist a unique function called the inverse function that's defined in the following way. Basically, if you take f of x and apply the inverse function to it, you get x. And similarly, if you apply f to the inverse function, you get the original value. Okay, so this is basically how you one way of defining the exponential function. Given the logarithm, it's the inverse of the exponential of the logarithm function. Sorry, and this is a result that will be reused quite a bit in maths, and probably proven at some point if you haven't already. And this is how it's used to define the exponential function. We reach the definition of the exponential. So it tells us the following. The logarithm, as I mentioned, is a bijection from r plus star to r. We denote its inverse function as exponential, and it satisfies the following properties. For any x in r plus star, you have exponential logarithm of x equal to x. Okay, it's really important here that this is strictly positive. And similarly, for any real value, you can take the logarithm of the exponential and you recover the initial value. So that's how we can use the logarithm to define the exponential. And in a similar way to above for the logarithm, we have a bunch of properties for the exponential function. And I don't think there's much that's new here either. So we have the following properties. So they're all quite standard properties. If you take a look at them, we have the fact that the function is defined, continuous, increasing on r. It's differentiable and even C infinite on r. So defined, continuous, and increasing on r, differentiable and C infinite on r. The derivative is itself, okay, which is quite a particular property. I think it's the unique function, or it is the unique function whose derivative is itself. You have the sort of opposite properties to the logarithm. So the exponential of the sum is a product of the exponentials. You have two limits. And then we have the following limit. So maybe I can detail point 5. the key to point 5 is this. So exponential of x minus 1 divided by x, that's exponential of x minus exponential of 0 divided by x minus 0, okay, which in turn, if you take x to 0, goes to exponential prime of 0. So that's just an extra step that's hidden here that you may want to add if you're wondering how to get from one step to the other. And I suppose what we can also do here is graph the exponential function. It won't do any harm to review its graph. So graph of x maps to exponential of x. Maybe one property that you can add is exponential of 0 is equal to 1, and that is due to the fact that the logarithm of 1 is equal to 0. So you just sort of invert that property for the exponential, and we can graph it. So it's defined continuous and increasing on r, and in fact it maps to r plus star. Okay, as the logarithm defined above maps from r plus star to r, the inverse function will map from r to r plus star. Okay, so our graph this time will be valued in r plus star, but we'll take values on the whole of r. So let's fix x and y. So what can we say? We know that the function's increasing, and we know that exponential of 0, if I put 0, 1, 2, minus 1, etc., and just 1 here, the curve will pass through the following point here, and we can compute the tangent to the function at 1. So I'll give the expression for the tangent in a minute, but try to compute the expression for the tangent, if you can, at 0. So are you able to compute this tangent?
Is it x plus 1?
Yeah, it's just that you're absolutely right. So if we have a look at how to get this tangent, so we know that, let's just list some properties that will help us graph. So the exponential function is increasing on r, and so exponential of 0 is equal to 1, and we can have a look at the tangent at 0. And the tangent at 0 is given by the following expression. So we have y equal to exponential of 0 plus the derivative of the exponential applied at 0 times x minus 0. Okay, that's just a formula for the tangent. This is equal to 1. This is equal to 1 because exponential prime of 0 is exponential of 0, which is equal to 1. And so if we sort of write out what this expression is equal to, it's 1 plus x. And so very roughly on the above graph, 1 plus x has the following behavior. And so you've got a tangent here, And one thing that's interesting about this tangent is if we have a look at something we proved yesterday, I think. So in example 6.17, we proved something relating to this tangent. So we proved in example 6.17 that for any x in R, exponential of x is greater than 1 plus x. So one thing that I didn't do in the logarithm function, but I'm going to illustrate for the exponential, is that as soon as you have a tangent, it's often a good idea to check whether you have some information on the relative position of your function and its tangent. So here we have this inequality, where this is our function that we're trying to plot, and this is a tangent. So what does it tell us about relative positions here?
It's probably on the left side of the tangent we just drew.
Yeah, exactly. So if we take a look at this graph, when we actually come to plot the exponential function, we never want to cross this line, okay? Because we could have it as we could have the following setting. If we just knew that it was a tangent, we could have something roughly, with a smoother line, but roughly like that. We know it's not the case here. So that will help us draw the curve. And one sort of final thing that we're going to use that's written in the properties above, the exponential function goes to plus infinity at plus infinity, and it goes to 0 at minus infinity. Okay, we could probably derive some further properties that would help us draw it, but we can get a rough idea of this curve right now. So if I try and do that, we get something like this. Again, it's a function that, as you probably know, goes quite quickly to plus infinity, and it also goes quite quickly to 0. So what I've drawn is a rough sketch of the curve of the exponential function. Okay, so those are two functions, that we've been able to review. And one further thing that we can do with these functions, which is quite useful, is compute some limits that are called croissance comparée in French, which can roughly translate as sort of growth comparison limits. So have you heard, have you sort of discussed croissance comparée before? Okay.
I don't think so, but maybe under another word, but it doesn't ring a bell.
Okay, no, it's possible that it's new. So what they are basically a bunch of limits related to the logarithm function, the exponential function, and sort of polynomial functions, and how they sort of relatively, I guess, behave with each other. So one thing that you possibly know is that the exponential function is generally quite a strong function. So for example, you have whenever you divide the exponential by a polynomial, okay, for example, exponential of x divided by x squared, you know the exponential of x goes to plus infinity, and x squared also goes to plus infinity at plus infinity. But despite that, despite the fact there's an indeterminate form, and despite the fact they both go to infinity, the limit will still be plus infinity. Basically, one rough way to describe it is that x squared, here if you have alpha equal to 2, isn't strong enough to basically counteract the behavior of the exponential. And so that's one example of sort of croissance comparée results, or growth comparison results. But there are a whole load of them, which are listed here. And what's quite interesting is that they can all be proven basically as an extension of this. So we're going to see how this one's proven, or proves, and see how we can then extend to these limits as well. So let's have a look at that. It's going to be based on the study of a particular function again. So the proof is in your notes, okay? In the first sort of part of the proof, is related to the first property. So where there's a first sort of point on the left, that's specific to the first property. Okay, and so the key, maybe I can write it up here, key to 1 is proving that ln of x is smaller than square root of x. Okay, that's basically the first step to this proof, and doing that is basically what we do in this proof up till here, and it's something that we prove for x greater than 4. Okay, it's not true when x is smaller than 4, but beyond that it is. So how do we prove it? Well, what we're going to do is study the following function. Again, as you can see, this function that we define as d is very closely related to this inequality. If d is negative, then this inequality will hold. So we're going to sort of repeat the type of process that we've done many times now, but this function is defined, continuous and differentiable on 4 to plus infinity. So of course, it's also defined, continuous and differentiable on r plus star, for example, but we're going to restrict our study to x greater than 4 because that's the values that we're sort of interested in. And so as it's sort of defined, continuous and differentiable, we can take x greater than 4, and noting in particular that the square root of x is greater than 2, then we compute the derivative. So the derivative of the logarithm is 1 over x, and the derivative of square root of x is 1 over 2 square root of x. Okay, so if we reduce this sort of difference of 2 fractions to one specific fraction, you get this. Okay, so maybe the intermediate step here that may not be that clear is that you get, first of all, you get equal to 2 square root of x minus x divided by 2 square root of x times x. And then as we're taking square root of x greater than 2 and x greater than 4, and in particular basically not equal to 0, we can simplify this expression here by square root of x. Okay, so if we do that, we reach this expression, and you can see why we may have chosen some sort of inequality related to square root of x and 2, because up top here, we see that the sign of this term is directly related to basically the sign of 2 minus square root of x, as 2x is positive. So 2 minus square root of x is negative when square root of x is greater than 2. So this function d has a negative derivative on 4 plus infinity, and it's therefore non-increasing on 4 plus infinity. And so what we can then say is that logarithm of x minus square root of x, if we take x greater than 4, it's smaller than the value at 4. And in particular, if you have a look at the value at 4, we reach 2 logarithm of 2 minus 2. That's smaller than 0, and that's through the fact that logarithm of 2 is smaller than 1. I don't think that's a property that you're expected to know at all, but it's something that we use here and that you'd be able to check. And so if we now use the fact that logarithm of x minus square root of x is smaller than 0 for x greater than 4, we get this inequality. Again, it's the thing that we wanted to prove, I mentioned above. And so if we come back to the actual limit, the actual thing that we want to prove this limit here. So the fact that the logarithm of x over x goes to 0 at plus infinity. And how do we do so? What we do is we take x greater than 4, and in fact we're going to take x quite big, okay, as we want to limit at plus infinity. And we're going to have a look at logarithm of x over x. The logarithm function is always positive, and we're taking x sort of greater than 4. So the term here is positive, so we get a bound on the left-hand side. And if we use the fact that logarithm of x is smaller than square root of x, we get an upper bound, which is written here. And you can simplify it by square root of x, and you reach 1 over square root of x. So in particular, the logarithm of x over x, for x big enough, is stuck between 0 and 1 over square root of x. And 1 over square root of x, you should be able to compute this limit at plus infinity. What would you get here at plus infinity?
0.
Yeah, 0. It's quite a simple limit to compute. And so your function is stuck between 0 and something that goes to 0, and so you conclude on this limit here. Okay, so that's the proof of the first property, and you see that the logarithm function is quite slow, I guess, at plus infinity. This thing goes to plus infinity at plus infinity. This thing does too, but x is basically stronger than logarithm of x. And so the whole ratio will go to 0. So that's the first croissance comparée result. And using this, you get, and sort of extending the reasoning, you get all the other results basically. And so the proof here is in your notes for each of the different points. So we can take a look at the reasoning that allows us to derive those results. So the second sort of bullet point is related to the second result. So this bullet point is for point 2. And it's a direct consequence of the previous result. So what we want is the limit of logarithm of x over x to the power alpha. And what we're going to do is set t equal to x to the power alpha. So t here replaces x to the power alpha, and logarithm of x, okay, will be equal to logarithm of t to the power 1 over alpha. That's just replacing the values by the values related to t, and then you can use the properties related to the logarithm function and see that this term on the left rewrites as logarithm of t divided by alpha times t. Now, the key then is that as soon as x goes to infinity, as alpha is positive, t goes to infinity. So here, to get this result, we just need to use the result related to logarithm of x divided by x, and it gives us 0 as well. The fact that there's alpha here doesn't change anything at all, basically. You just end up with a constant that's positive in front of the limit. So it's still 0 plus. Okay, so similarly, that's one extension, and similarly, we can extend it to basically whenever we have powers. So whenever we have logarithm of x to the power beta over x to the power alpha, where alpha and beta are positive, we can basically rewrite it under this form. So that writes as logarithm of x divided by x to the power alpha divided by beta. And so all of that is the power beta. But as soon as alpha divided by beta is positive, okay, the thing that's inside using the result above will go to 0, and 0 to the power beta with beta positive still goes to 0. So that's a proof of point 3, okay, which you can see is still based on this fact. And then we've got some more. So one is related to the exponential function. So points 4 and 5, if we take a look at what their expressions are, they're related to the relative behavior of the exponential and polynomial functions. So let's take a look at how they're derived. So in the first case, we have exponential beta x divided by x to the power alpha, and in particular, if you set beta equal to 1, okay, it's this limit. So I guess this limit is sort of included in this one. So what do we get here? We're studying this function, and we're going to want to use the result related to logarithm of x over x. So we want to sort of bring ourselves back to such a result. And we're going to do this by the following sort of change of variable. So we're going to set y equal to exponential of x. And as we're looking at the behavior at plus infinity, as soon as exponential of x goes to infinity, y goes to infinity. So the limit properties are conserved. And in particular then, if we do this transformation, we'll end up with y up top. And at the bottom, we'll be left with logarithm of y to the power alpha, because as soon as you have this, then it's equivalent to x equal to logarithm of y. And so here we have a term related to y up top and logarithm of y at the bottom with different powers, and y is going to plus infinity. So we don't quite have this, or this in fact, but we have 1 over this. But as we know that logarithm of x to the power beta divided by x to the power alpha goes to 0 plus at plus infinity, if you take the inverse, you'll get plus infinity. So you get 1 over 0 plus, which sort of is plus infinity. Okay, so that's how we get this property. And I mean, similarly, comparing x to the logarithm, there's a similar reasoning in the proof. You just bring yourself back to this. So the final bullet point is for point 6. So you can see that all of the properties, the proof is based on this first result, which is based on curve sketching, or computing the variations of logarithm of x minus square root of x. So these properties, from what I've gathered, then they're new for you guys. And they're really useful properties that you sort of need to know. Now, 7 properties probably seems like a lot, but if you take a look, there are actually only, I think, 3 here. So you've got 3, which includes 2 and 1. Okay, if you look at it, you've got 5, which includes 4 and 5, and then 7 includes 6 and 7. So you need to know basically 3, 5, and 7 going forward. And you can sort of remember it by, I guess, remembering this sort of not very mathematical idea that logarithm is weaker than polynomials at plus infinity. The exponential is stronger than polynomials at plus infinity, and the logarithm is stronger than polynomials at 0 plus. Okay, and by stronger, that you then know that that's a function that takes over at plus infinity or at the limit. So here 0 plus. Okay, so those are some new, very useful properties that you're expected to know going forward. And so the proof of those properties.
Can we use these directly in a test, or do we have to prove them beforehand?
No, absolutely. You can use these anytime you want going forward. You can use them, and you'll find that they'll be really useful in lots of situations. So yeah, definitely learn them and definitely use them if you need to use them at any time. Okay. And those properties will conclude this part on the logarithm and the exponential function, which are 2 sort of key functions. And you can see that the key, or the only, the new thing is this proposition here with 3 new limits that will be quite useful. Now, the second type of functions that we're going to review are trig functions. So, you know, sine function, cosine function, and perhaps the tangent function too. So that's what we're going to review now. So did I give a title to the different parts? Okay, I gave a title to the logarithm part. I didn't to the exponential part, but I'll put it. So we saw the logarithm, the exponential function. So if I just squeeze that in here, and then the last things that we're going to review here are some trig functions. So let's take a look at these trig functions. So you should know 3, and perhaps 2 better than the third, but you should know the cosine and the sine function. So maybe a first thing that we can mention very briefly is how are they defined, because we sort of discussed the definition of the exponential and logarithm function. They're basically definable in several ways, I guess. I think one historical way that they were defined was using the trig circle. So basically, if you take a look at this paragraph where there's a mention of the definition of basically how they were one day defined, if you want to define them rigorously, we need to define an object which is the exponential of a complex number. We touched on this in the chapter on complex numbers, but didn't sort of define such objects that rigorously. But if you admit basically that this number sort of exists, that you can apply the exponential to complex numbers, then you can define the cosine and sine functions as follows. They're using the Euler formula. You get this definition for the cosine and this definition for the sine. And I suppose it doesn't really help you to see what they're like that much, because here you've got exponential of IB and exponential of minus IB, and we don't really know with the maths that we've done so far what these objects are. But that's historically how they were defined. Somebody came up with this idea of the exponential of a complex number and then defined the cosine and sine through the following formulae. And then we're able to use these expressions somehow to derive properties for these functions and trace them. But as you can see, it calls for the introduction of objects that we haven't seen yet, but that's how someone someday decided to define them. And there are probably other ways, in fact, to define them. So let's first review the cosine function, which you've seen probably many times before. So the cosine function verifies the following properties. So the first thing is that it's defined continuous and differentiable on R, and it's even C infinite on R. And you know that its derivative is minus sine, and equally you know that the derivative of sine is cosine. So if you keep deriving cosine, one time you'll be related to the sine function, and the second time you'll be related to cosine again. You know that the function is 2 pi periodic, so if you add 2 pi to the value inside your cosine, you'll be equal to the initial value, and it's an even function. And you should know the following properties. Hopefully you know some of these already, but these are quite useful, and as you know, we don't use calculators in maths in higher education, or at the moment anyway. I don't think you will ever much if you do sort of the maths specialization at INSA. So these properties are really useful to know. And again, like the limits that we mentioned, you can just use these properties when you know them. Again, in particular, they relate different sort of shifts in cosine to trig functions. So those are some properties. And similarly, we've got properties for the sine function. Okay, so you've got the following property. Okay, so similarly to cosine, the sine is C infinite on R. The derivative is just cosine. It's 2 pi periodic, sorry, is odd. And you've got very similar properties here as the ones above. Okay, one thing that we can do is just trace the graphs of these two functions. So we know that they're 2 pi periodic, so actually maybe we can just trace what happens on 0, 2 pi. Yeah, we'll do that. So let's try and graph cosine and sine. So we know that they're 2 pi periodic, so we can just have a look at what happens on pi. So if I place pi here and minus pi here, yeah, and so we can look at what happens on the 2 pi interval is what I wanted to say. So let's start off with the cosine function, which is the first one that we mentioned. So what's the value of cosine at 1? Oh, 0, sorry.
Oh,
Well,
that's 0.
Yeah. At 0, what is it?
1.
Exactly, yeah. So at 0, it's equal to, actually, I'll change the, I'll put 1 here on the y-axis, then we'll be able to see better. So at 0, it's equal to 1. Are there any other values that you know?
For minus pi and pi, it's also 1. Oh, no, for minus pi, it's -1, and for pi, it's also -1, sorry.
Exactly, yeah, no problem. So you get these values. So you can see that it's somehow going to pop from -1 to 1, and then from 1 to, oh, that's -1 at the bottom, -1. Do you know any other values in particular where it may cross 0?
Pi over 2 and minus pi over 2.
Exactly. So if I try and place these here, so halfway through here, you've got minus pi over 2 and pi over 2. And you know that the function is going to pass through these points. So maybe we can now compute some tangents that will help us sort of graph this function. So first of all, let's have a look at, some tangents. So and these are tangents for, we're doing the cosine function, yeah. So we're doing some tangents for cosine. So maybe first we can have a look at the tangent at 0. So at 0 you get, if we apply the formula, y equal to cosine of 0 plus cosine prime of 0 times x minus 0. So cosine of 0 is equal to 1. Okay, we said that a minute ago. And cosine prime of 0 is equal to sine of 0. And that's just equal to 0. So the tangent is simply a constant function equal to 1. So I think this graph is going to get a bit messy, but you get basically a horizontal tangent like this. And using similar reasoning, you can prove that at pi and minus pi, you'll get y equal to -1. Okay, you'll get the similar formula to this. So cosine of pi plus cosine prime of pi times x minus pi, and the sine of pi should be equal to 0, and the cosine of pi will be equal to -1. So in these two values as well, you've got a couple of basically, no, that's not the right green. You've got a couple of horizontal tangents. Okay, and maybe one final tangent we can look at is the tangent at pi over 2. So at pi over 2, we get cosine of pi over 2 plus cosine prime of pi over 2 x minus 0. So this here is equal to 0.
I think it's x minus pi over 2.
Oh yeah, thank you. Come on, erase. Yeah, you're absolutely right. Thanks for that. And so we need cosine prime of pi over 2. Oh, that's a minus. And so we get minus sine of pi over 2. But what's sine of pi over 2?
1.
1.
Yeah, absolutely. So this here, if we then use the minus sign, that would give us -1. And so y will be equal to pi over 2 minus x. Okay, so if we have a look at what that means for this drawing, very roughly, we need to get a curve that's of slope basically minus x. So, and here, due to the fact that the function is what is it? It's odd. You can draw the sort of symmetric behavior at minus pi over 2. So if we then try and draw the graph, this is probably going to be a bit messy, but you'll get something like this. And it's depending on the scale of everything, it'll probably be rounder if you get a good scale. But that's the behavior roughly of cosine on where is it, on minus pi. Okay, and this is a rough graph of C of cos, so the curve of cosine. So then if we want to graph the sine function, there are two ways of doing it. We can sort of repeat this sort of procedure again, so computing some tangents, etc. You also know, if you just use this property, that you just need to shift basically this curve by pi over 2. So we can graph sine. So using the fact that for any x on R, sine of x minus pi over 2 is equal to cosine of x. So of course, another thing that we can mention here for this one is that you can just keep repeating this pattern and you get the behavior of cosine on the whole of R. But if I take this, what we can try and do is use it to give the behavior of the sine function. So I don't know if I'm gonna, yeah, I'll try and do it like this. So we're gonna have roughly the same behavior, if I manage to not erase everything. So basically the rough behavior of the curve is going to be the same, but not at exactly the same points. So we need to shift the curve by pi over 2. And so, for example, we can have 0 here. Okay, if we have 0 here, you'll have pi over 2 here, pi. And you can see that I need to just continue the drawing on one side. So I can just extend the curve a bit on the left. And very roughly, hopefully, reach minus pi, and we'll have minus pi over 2. Okay, so the tangents and everything are still roughly the same, but the sort of curve is shifted basically by pi over 2. And in particular, we have sine of 0 equal to 0, sine of pi over 2 equal to 1, minus pi over 2 you get minus 1 normally, and pi and minus pi you get 0. Okay, so we get C of sine. And we've done the behavior of sine on minus pi. Okay, so that is a rough sketch of the behavior of the sine function. And so one thing that we can note, if we want to, related to the cosine and sine function, is that if you're ever given this differential equation here, okay, then as basically if you derive sine once, you get cosine. So if you derive sine twice and you use the derivative of cosine on the right, you'll get the second derivative of sine equal to minus sine. And so the sine function verifies this differential equation, and through similar reasoning, the cosine does too. So basically, one other way of defining the cosine and sine function is through a differential equation. But that's just sort of a side note, sorry. basically there's not one single way to define these functions. So there's the way through the complex exponential, there's a way through the differential equations. In any case, they're quite abstract ways of defining a function. Okay, you're sort of supposing that a solution to this differential equation exists. You can, for example, call it the cosine, and then somehow through this differential equation derive all the related properties. But of course, doing that process is beyond things that we do at the moment. So that's it for the sine and cosine. And one function that we can finish off with today that's related to these functions is the tangent function. So I'm guessing that you probably have done less on the tangent function than on sine and cosine, possibly. It basically comes up a little bit less. So the tangent function is basically defined as the quotient of sine and cosine, but only when it's well defined. And I think at some point in this chapter, where was it? I think it was when we were discussing variation tables, possibly, or defining the study space. So right at the start of this chapter, we gave the definition domain of this function. And so basically this function is well defined as soon as cosine is not equal to 0, and cosine is equal to 0 at pi over 2 plus k pi. So as cosine of x is equal to 0 for x, I'll do it like this. That's equivalent to x equal to pi over 2 plus k pi for some k in z. The function x maps to tangent of x equal to sine of x divided by cosine of x is defined for x in R, from which we remove pi over 2 plus k pi, where k is an integer in z. Okay, so that's the first property related to the tangent. So in particular, that gives us a definition domain, and we have the following. Okay, so the definition domain that we've just stated can be rewritten like this. We basically take the union of all of the intervals, all of the open intervals in R that are between sort of two values that write like this. We can prove that the tangent function is pi periodic and odd. Okay, to do that, you show that tangent of x plus pi is equal to tangent of x. And in particular, you can use these properties here. Okay, as sine of x plus pi and cosine of x plus pi are equal to minus, say, sine and minus cosine, then that gives us the periodicity of the tangent function, and it's odd. Okay, that's related to the fact that the sine is odd and cosine's even. The tangent function is differentiable on the definition domain. Okay, so on each of these open intervals, you can derive the tangent function, and the derivative is 1 plus tangent squared. And you've got the following limits. So on each sort of edge of these intervals, you've got some limits. On the right-hand side, you go to plus infinity, and on the left-hand side, you go to minus infinity. And you've also got a certain limit. You know that the basically the derivative of tangent at 0 is equal to 1. So you've probably seen a curve of the tangents before, but you basically get something that's roughly like this. If we place this 0 here, x, y, And if we say that here you have pi over 2, is that going to work? Yeah, there we'll have pi over 2, and here we'll have minus pi over 2. Okay, the function is going to basically be defined up until this value excluded, and up until this value with this value excluded. Okay, and here it's going to go to plus infinity, here it's going to go to minus infinity. And one way that we can maybe gain some further information on the function is look at what happens at 0. So tangent of 0 is well defined. Okay, it's equal to sine of 0 divided by cosine of 0. And so what's that equal to?
Zero.
Yeah, absolutely. As the sine of 0 is equal to 0, that's equal to 0. And we can have a look at a tangent to the tangent function. So tangent to tan at 0, so you get y equal to tan 0 plus tangent prime of 0, x minus 0. And so we've just shown that this is equal to 1. Oh, sorry, the first term is equal to 0. And here, the derivative at 0 is equal to 1. And so you get y equal to x. Okay, so if I place, say, pi over 2, say the pi over 2 is here, and minus pi over 2 is down here, so there's sort of I can plot x quite easily then. So y equal to x has roughly this slope. I think you can prove something along the lines of the behavior like this, which is, wait a minute, isn't that great? So you've probably got something like this where that slope becomes vertical and that slope becomes vertical too. That's a sort of a very rough graph of what happens with a tangent function. Of course, for it to be more precise, one things that one could perhaps do is study the relative slope of tangent and x, and you can probably derive some properties related to that. That would make the graph more precise, but roughly you've got that. And as it's pi periodic, you can do the behavior on the whole of R by shifting this curve. Basically, here you'll have this, and then here you'll have the same, and here you have the same thing. So this is roughly C of tan, and so this is a rough sketch of x maps to tangent x on minus pi over 2, pi over 2. Okay, of course, this isn't the whole behavior on R. You'd have to complete, sort of complete the graph to get that. Okay, what time is it? Okay, it's 12:15, so we're done. I just want to remove that. Yeah, that's a rough sketch of the tangent function. And one thing I can just say before we go is that if you look in your notes, there's some further properties for the tangent function that I can perhaps paste. And to be honest, I don't think these will be used as much as the ones for the sine and cosine. And in fact, you can prove these using the properties for the sine and cosine. So perhaps we'll take a look at the proof of some of these in the next class. And one thing I just wanted to mention is that all of the rest of this sort of subsection related to functions, and that's on hyperbolic functions, is in your notes as sort of theory, but it will be discussed in a tutorial with classes. So in tutorial classes, we'll have a look at these functions and prove all of these properties here. So I won't say anything about that today or in the following classes, but we'll do it when doing some exercises. Okay, if that's okay for everybody, we'll stop here for today. Okay, so I'll get the notes to you as soon as possible, but that's it for now. So